Morning. Sound okay in the back there? Awesome. Okay. My name is Chris Lutes. I'm with Jacobs Engineering, representing a large team here, including RTI International and EPA ORCR in doing this work. So the outline. Our principal problem is that we have sparse data, 2, maybe 4 rounds of 24-hour samples typically to make decisions about individual buildings or even to start making decisions about whole neighborhoods that may be impacted by vapor intrusion. We're going to talk here about the benefit of what we call indicators and tracers. Those are simple, low-cost measurements such as radon, temperature, or differential pressure. I'm going to take most of my time today to present 3 different analyses where we've looked at large data sets and tried to get our hands on whether indicators and tracers are doing this good. First, we're looking at the conditions leading up to the observed peak values. So you can imagine this as looking up in the sky and seeing what the sky looks like and saying it's going to be sunny tomorrow. Then we're going to look at the probabilities of observing what we call reasonable maximum exposure using conventional sampling techniques, either randomly or seasonally timed versus indicator and tracer guided. And then we're going to flip the question around a little bit and say if we set a standard for needing a given amount of protection, a given amount of certainty, how many samples does it take to get there? Or can we get there with a decision guided purely by the radon data? And then we're going to look at where we are in terms of guidance and additional data collection. So, summarize, the key problem here is that we have very sparse data at most of our vapor intrusion sites and highly skewed concentration distributions that make it very hard to make good decisions. So the vapor intrusion field has taken a limited number of lessons from the radon field. It's taken a lot of its basis, but the depth of understanding, I think, is pretty limited. So everybody who does vapor intrusion thinks they know only a couple of things. They think they know that stack effect makes winter worst, and they think they know they should sample with a summa canister. That's essentially what the average vapor intrusion consulting project manager knows about vapor intrusion. Of course, I think many folks in this room know that its story can be more complex than that when we have high stack effect driving force bringing soil gas into the building, we can also have high air exchange rates. If you think about it, VOCs, if they're present in shallow soil directly below a release building, can be significantly influenced by the temperature of that soil. The idea that 24-hour summa canisters are the way to go for sampling is not particularly endorsed in the EPA 2015 guidance document, but it's essentially what everybody knows how to do. The 2015 guidance document says, we'd like to have longer-term samples if we could come up with a good way to do it. And the 2015 VI guidance gives you only a very little bit of information about how many samples to take. It basically says you should take more than one. More than one. Well, that leaves a lot of choices. What is typically done in the field is 2 to 4 rounds before people make a decision. And if you had 2 to 4 rounds, and the distribution of concentration observations was symmetrical, you might not be so bad off, because you'd have a chance that you'd get some measurements over the mean. So you'd have some idea, perhaps, of long-term cancer risk. But the reality is that we don't have symmetrical distributions. We have distributions that look much more like this. Let's see if I do my laser pointer okay. Where most of the observations are below the true mean of the distribution. And even worse, when we get into worrying about non-cancer effects, we're going to be focused on upper ends of the distribution, and in this talk we're going to focus on the 95th percentile as an upper end measurement. The VI guidance actually says that the reasonable maximum exposure is between the 90th and the 98th percentile, someplace in there. So if you're looking for that 95th percentile, you've got a lot of chance that all of your samples are going to be well below that 95th percentile. And we don't know that this is the true shape of the distribution. It could be even funkier than this. It could be even more skewed. So here is a real distribution. On the left side is TCE concentration. This is Paul Johnson and Chase Holton's data, published back in about 2014 from a house called Sun Devil Manor in Utah. The blue dots in here are the individual observations over several hundred days of detailed sampling. Again, the concentrations in a log scale, 0.1, 1, 10. Then days are on the x-axis. Here's the mean of the observations. But then if you ask the question, what percentage of the observations provide half of the total exposure? It's actually the ones at and above this line. So now it's really hard for people to get their heads around that concept. And the best way that Laurent, my colleague, has come up with to get ready to that concept is that if you ask what is the average income of the United States, people will give an answer, $100,000, right? And then if you ask how many people in the United States get 50% of the total income or have 50% of the total wealth, I think you can start to count them on your hands. Buffett, Gates, Zuckerberg, right? You're not going to need very many people to have 50% of the total income in the United States. And that's what this is saying, is that over only 25 days out of a total observation period of 723 days accounted for 50% of the total dose of TCE in this very skewed distribution. So this is another way of looking at those distributions. Here's that same distribution I just showed you on the left side. Again, a log axis, a box and whisker plot, 25th percentile, 50th percentile, 75th percentile. And then here what I've shown in the red is the 90th percentile. In green is the 95th percentile. And then the red triangles are the 50th percentile or 50th percent of the total exposure. And you can see that the 50th percent total exposure point is usually above the 75th percentile. Indeed, the mean of these distributions is often above the 75th percentile. Just to give people a quick tour here, these four boxes are from the EPA's Indianapolis duplex study. These two are a commercial building near Moffett Field. These four up here are from a building that the Navy actually ended up essentially evacuating because of vapor intrusion concerns in Virginia. These two up here are from David Barnes' study in Alaska. And these four down here are from a currently occupied vapor intrusion case study in Virginia that we are going to talk more about later today and also later in this presentation. Let me just draw your attention here where we've got a large data set, 392 samples, or back here on this data set, 723. We got a lot of observations that are way up here. Now, people might usually start to say, that's crazy. Those are wrong observations. Those got to be outliers. I'm going to toss them out of my data set. But we are very convinced that those are real observations there, and Dr. Johnson is very convinced those are real observations at Sun Devil Manor. Now looking at the same problem, except in time, here we're going to look at it in space. This is a Superfund site in the western United States. The groundwater flow is coming in this way and sort of splitting. This is about 4 miles down gradient from the source. The green and yellow show the concentrations. Green and yellow shading show the groundwater concentrations. This is a busy slide, but I'm going to ask you to look at the dark blue squares, the yellow squares, and the white squares. So the white squares are all the samples, all the houses that were sampled that didn't have any results above the screening or action level. The blue squares are the houses that were sampled where we're darn sure it was vapor intrusion and it was above the action level. And the golden squares are ones where we're moderately confident that it was vapor intrusion. And so I think the thing to take away here is how scattered those blue and golden squares are across this map and how little insight you get from the groundwater concentration map to where those are. And indeed in this area here, it's been shown that a lot of the vapor intrusion is attributable to preferential pathways, in this case from land drains, areas where land was drained to make good old agricultural land into good land for houses, or make agricultural land dry enough to grow crops. So why do we care about peak concentrations? Short-term peak concentrations can dominate the long-term cancer risk, and we have concerns about short-term exposure for certain constituents of concern, for example, TCE. Now, can we see this 95th percentile concentration with our small number of samples? Well, simple math tells you if you get one sample, you got a 5% chance of seeing the 95th percentile. If you have 4 randomly timed samples, you're up to a big 18% chance of seeing the 95th percentile. Still don't have much chance of seeing it. In order to be able to see the 95th percentile with 95% confidence that you've seen it once, you got to take 58 random samples. Nobody can afford to take 58 samples at $300 a sample. So our current VI assessment processes are too complex. We use too few samples to support clear decisions. They're expensive, slow, they're disruptive. Remember, these people haven't asked for us to come and sample, and they get very tired of consultants knocking on their door the 6th time. And so we need a better way. I'm going to talk today about a few data sets scattered around the country. Sun Devil Manor is here in Utah, the Indianapolis data set here. Interestingly, those are pretty much the same climate zone. The Virginia sites are down here. Also going to talk about sites up in Alaska, up in Fairbanks, Alaska. Let's see what we can do here. All right, our first analysis. Going to be only able to give people a quick flavor of these analyses, so I've provided references where you can dig into them more. I can provide copies of this to anybody who's interested, paper in groundwater monitoring and remediation. So what we did here is we ranked all the concentrations from a set of 492 daily observations and took the 95th percentile and said, okay, we're going to keep our eyes on those 26 observations that are above the 95th percentile. And then we looked at our candidate indicators or tracers. So here we're looking at our temperature, and we're looking at where on the temperature curve, temperature distribution, those 26 observations occurred. So we're matching up the conditions under which the peak PCE concentrations occurred to the corresponding indicator data. And then we go back in time and we say, okay, here we've got an event represented by the red line on a data set of PCE or on radon or another variable, and then we go and say what was happening 24 hours ahead, what was happening 2 days ahead. And then we combine all that data into box and whisker plots to talk about what was typically happening a day or two ahead of our events of interest. See if I can advance the slide here. Come on. Let me see if I can get to go with this one. Come on. Okay, got it passed. All right, so in these box and whisker plots, let's look at the one in the blue in the upper left-hand corner. So now we're looking at hours before the event, 3 hours before the event, 6 hours before the event, 9 hours, and 12 hours. And so that's the event right over there, the peak PCE concentration, 95th percentile event. And then we looked at, does radon give us a good signal coming into it? Well, maybe not, but it gives a fairly decent signal at the time of the event in this data set. Following over here, the blue, one really notable observation is that the event seems to be predicted by low wind speed. That makes perfect sense here because what we're dealing with is a 1910 house that is leaky as a sieve. So low wind speed probably translates to low air exchange rate, high PCE concentration. And you can see diminishing wind speeds 12, 9, 6, 3 hours in. Similarly, we did the analysis on days. So that's 4 days before, 3 days before, 2 days before, 1 day before, and the day of the event. So the PCE is going up. You can also see that the radon does seem to have a trend going up. Looking over here, again, we can see a trend of the wind speed going down. Some perhaps association with colder temperatures. Our data actually analysis, more in-depth analysis suggests that it's temperature getting colder is more important than temperature being cold. One more data set from that analysis. This is what we call Virginia Site A. It's a large military building. It's essentially a room within within that building. It's essentially built out within a warehouse. Here you see the TCE concentration going up in the hours before we call it an event. You see that there's no relationship in the subslab TCE. Indeed, the events seem to be associated with below average subslab concentration, but we see a really nice correlation here at this site between radon and TCE in the hours coming into the event. So this would say radon is a useful tool telling us to be alert to a high TCE concentration coming, or that we have an opportunity to sample for a high TCE concentration. Here you can see wind speed is not very useful, but that the high TCE events were associated with a well below average temperature, but not perhaps the most cold temperatures. So we looked at 5 or so sites in this way. We found that in every case we had one or more indicators that were decent as a predictor that high VOC concentrations were coming, but unfortunately they weren't the same indicators. We didn't know ahead of time which indicators were going to be, or tracers were going to be ideal. So we need more understanding of what we call in the vapor intrusion business the conceptual site model, the general pattern of what's going on. And we believe that there's a significant difference here between places where we have the mass of VOCs right under the floor because we spilled it in that building versus places that are way down gradient on a sewer line or down gradient of a groundwater flow. So then we turn to looking at probabilities of success with various sampling strategies. So this graphically shows these sampling strategies, how we march through this analysis. So we have large data sets from research sites with a lot of samples. And we make a decision about how to sample. We either use the calendar, like many of our guidance documents tell us to do. We do it randomly, like we do in the real world, because we often sample when the check comes through or people are willing to let us in the door. Or we can use indicators and tracers as illustrated here by this thermometer. We take small subsamples, 2 to 4 subsamples, and we say, have we seen what we want to see? What's the chance that we've seen what we want to see? So these are the data sets. I'm not going to belabor this since we got a late start today, but we have data sets with hundreds of samples down to the Gaffney data set has 27 samples. Still a lot more than we have in the real practice. So we looked at a bunch of different ways of scheduling when we could sample. A lot of guidance documents tell us to take one sample per calendar season. We could try taking just half in the heating season, half not in the heating season. We could use all our samples in the heating season. We could make decisions based on change in temperature or indoor-outdoor differential temperature. We could make decisions based on differential pressure, or we could make decisions on sampling based on certain factors of radon. We ended up using mostly this concept that we'd take a large radon data set, either a whole year or at least a month, and then we'd start looking at at sampling when the radon was above its 90th percentile for that given building. It just goes into a few of the assumptions in our analysis. I'm going to skip it in the interest of time. So we're asking, essentially, can we get 95% confidence in making the decision we want to do? And can we come up with sampling strategies that we can apply the sampling strategy based on what we know when we drive up to the building or look at it on Google Street View? We're going to assess our strategies based on, do we see over the true mean, which we care about for cancer risk? Do we see over the 90th or 95th percentile? And then we're going to also look at what if we give ourselves a fudge factor of 3.3. Either say multiply our answer by 3.3 or divide our answer by 3.3 to give us essentially an order of magnitude range around our target. And the reason we do that is that we know that the toxicity numbers that go into our decisions are really uncertain as well. And so they're at least as uncertain as that. So maybe it's not such an unreasonable thing to give ourselves a multiplier around the target. Here we've got 120,000 square foot historic building, goes back to the Second World War. It's got these zones built out within it, office spaces within this larger warehouse that I think were just added on if somebody needed something. We have 18 months, actually a year of 2 years of high frequency observation in this space. Okay, let me walk you through this busy slide. And Kyle, how am I doing on time?
About 12 minutes.
12 minutes, all right. So we're looking at probabilities of success on the left side. Here we're looking at a set of 4 samples, and we're asking, can we get over the 90th percentile with 4 samples? What's our chances of seeing over the 90th percentile? Let's just focus in on the purple, which is 1 sample per calendar season. We got a really lousy chance, about 30% of seeing over the 90th percentile with 4 samples. If we use our radon-guided approach, shown here in the gold, it gets us up to about an 80% chance of seeing the 90th percentile with 4 samples. We did the same analysis with looking for the 95th percentile. It's not surprising. It's a lot harder to see the 95th percentile. Again, the radon strategy or the sample only and heating season strategy are the most successful. And of course, then if we give ourselves an order of magnitude fudge factor around the target, then we can be really confident that we're gotten at least that good if we use either the sample only and heating season or the radon-guided approaches. This is the Indianapolis duplex I mentioned to you earlier. Dates back to at least 1915. Big old leaky building. Low concentrations VOCs in deep soil and groundwater beneath it. Again, we'll look here just at the bars representing the 4 sample distribution, looking for the 90th percentile. A really lousy chance if we only use the calendar to guide our sampling. Only a moderately better chance, maybe up around 50% using radon or sampling only in the heating season. And again, if we give ourselves a 3x fudge factor, we got a lot of success. Same site, just using the daily data in the interest of time, I'm going to move on. Again, I can share these slides. All this was presented in much more detail at AEHS and is available online. This is that Sun Devil Manor I mentioned to you, a split level modern home, again sampled to death. Let's look here at the percentile change of getting over the mean with 4 samples. Again, seasonal sampling only gives you a really moderate chance, maybe about 50% or less, of seeing over the mean. The radon-guided approaches do significantly better. Then over here is the chance of seeing over the 90th percentile. Again, the radon-guided examples and the sample only in heating season are some of the better performers there. So summarizing across multiple sites, sampling 4 times based on differential pressure or temperature performed fairly well. 4 times in heating season worked really well at most sites. It gives absolutely the wrong answer at a site that I'm not able to show you here today because of time, which is up in Fairbanks, Alaska. It did really lousy in Fairbanks, Alaska, and that's because VOC volatility was controlled by soil temperature. So we have to know something going in to select our sampling strategies. And the sampling strategies with radon guidance generally worked pretty well at observing the upper ends of those distributions. Finally, this is the analysis we're doing right now. We're looking at the difficulty, how many samples we have to take, and ultimately the cost of providing equivalent protection using either conventional sampling strategies, random sampling or seasonal sampling, indicator and tracer guided sampling, or a concept of just going to mitigation based on demonstrated soil gas entry into the structure and the presence of VOCs in the general area in soil gas. So what we're doing essentially is what they call a bootstrap analysis, counting how many samples we have to take to get to the level of confidence, say a 95th percentile level of confidence, that we've observed a certain VOC concentration that corresponds, say, to a 10 to the minus 6 risk or a 10 to the minus 5 risk or a 10 to the minus 4 risk. And similarly, that we've observed concentrations corresponding to the hazard quotient we use for non-cancer risk. Let me just say very briefly, I'm not presenting a lot of results from this because we're still working through it, but the answers that we're getting out of here is, one, that the answer depends a lot on the shape of the distribution, which strategy is going to be the best strategy. And 2, that in order to use radon as our guide, we need to be able to interpret radon concentrations that are quite low if we have really strong VOC concentrations. So in those buildings that where we have VOCs released directly below the floor, if we have a radon concentration even up around 1 or even less than that, that can still be indicative of enough soil gas intrusion to be problematic. So we need pretty sensitive ways to discern the difference between ambient radon levels and true radon levels. 5 minutes, that's fine. We're closing in here. So our goal here is to see if we can come up with a strategy for making site assessment decisions that are simpler, less disruptive, uses these continuous indicator and tracer measurements, actively involves the citizens, occupants, so that they have a greater degree of trust, and that we make decisions rapidly. We're not there yet as a national matter of guidance. We do have state-level guidance documents that do endorse these concepts, at least partially. I see a few examples there from Oregon, North Carolina, Alaska, and Cal EPA. The Department of Defense has begun to adopt these approaches. And we have a very large study underway here in Fairbanks, Alaska, where we're looking at 7 different buildings and trying to compare both commercial institutional buildings to residential style buildings and how they perform for radon and VOCs over the long term. I appreciate everybody's patience with all the technical stuff. I'd be very glad to talk to you about this later. I am going to be talking this afternoon and going into a little more leisurely technical depth in the Indianapolis and Virginia case studies in the afternoon's talk.